Hi, everybody. Welcome to the Impact at Scale podcast with Zal Dastur. I'm now coming to you. If you notice a difference in my voice, it's because I'm actually in this fantastic new studio from the Great Room at Afro Asia in Singapore. They very kindly lent me space to record these podcast episodes. So, big thank you and a big shout out to the Great Room. My guest today is Fred Jordan, the co founder and co CEO of FinalSpark. Hi, Fred.
Hello, how are you?
Great to be here with you, Fred. I'm so curious because when you reached out to me to talk about your what you're building at FinalSpark, it sounded very fascinating. So, can you give us a bit of an intro into the project that you're working on?
We are trying to create the first living processor.
And so, tell me what you mean by a living processor.
So currently, everybody knows about digital processors. Okay. And the idea behind what we're doing is to use living neurons to perform computations. So actually, the processor is going to be really a living entity.
This is basically a replication of the human brain.
Yes, it's a direct application of what we learned the past 50 years about the human brain. Yes.
And you had talked to me before because I think the first question I had for you when you reached out was about, oh, this is incredible. How does it have an impact on the climate? And you were talking about energy consumption. So can you just share a little bit with me about the energy consumption and the sort of power of the human brain versus sort of the computer brains that we have now?
Yes, I think there is something I love to use is to compare the energy that we use compared to what we would use if we make a stimulation of our brain. So if I consider your brain, for instance, it's typically 100 billion of neurons. Okay. If I wanted to make a digital simulation of your brain, it would take a small nuclear plant, okay, with digital processors. This is in the state of the art today. This is what I would need, okay. But your brain right now is consuming 20 watts. So it seems at first glance that using digital computation is not really efficient at all. And we are talking about a factor of about 1 million. So it's huge. You know, we live in a world where people are fighting to get some savings of energy of 10%, 20%. We're talking about a factor of 1 million. This is totally disruptive.
It's fascinating, and the fact that what you said, to have a computer that is as powerful as my brain, you would need a small nuclear plant. And my brain functions on what I had for lunch and dinner,
Yes.
which seems like a much more efficient use of energy as well, regardless of the amount of output, but even the way it's able to transfer food into energy in probably one of the most efficient ways. I think probably something we don't acknowledge enough. We take it for very much for granted, the power that we have in our mind.
Yes. And you know, here, these are conservative numbers actually, because your brain is not only functioning, it's able to learn. And if you look at AI today, one of the big spending of energy is also on the learning. And on the learning, some figures indicate that we are more than 1 million more efficient, maybe like 1 billion more efficient in the learning process. So it's totally different views on the computation when you start to use living neurons.
Well, it's very interesting that you mentioned that about particularly the learning, because AI is obviously huge buzzword these days, and every technology company and everybody wants to be involved in an AI. And I understand that certain companies like Microsoft and others have actually wound back some of their climate commitments because their realization is that if we are going to build our AI functionality or our AI teams, the amount of resources that will be required in terms of the energy consumption is going to be huge, and we're not going to be able to hit net zero emissions. So obviously this plays a really large part in the future of technology.
Yes, yes. Actually, in the current situation, we have a limited amount of choice. Okay, if we want to grow with AI, so either we find a wonderful way to create energy which is not polluting anything. We've been looking around for quite a time, and it's not available yet. Or we find a way to make the same kind of computation for much less energy. So then there are not so many ways around. So yeah.
Fred, this sounds something, incredibly complex. What makes you the right person to solve this problem?
Oh, no. I'm not sure I'm the right person to solve this problem. I just happen to be with the right set of. There is about luck here in my personal history to be in this place. But I have a PhD in signal processing. So all my culture actually was, until 5 years ago, 6 years ago, I would say, was about digital computing and AI. This was my thing. Okay. Starting with computers when I was like 12, this is my life. Okay. And I don't know if I'm the right person, but 5 or 6 years ago, we realized that with digital computers, there was no way we could end up with something significant if we try to simulate neurons like our neurons because of the energy consumption I mentioned before. Okay, this was just nonsense, and the alternative was to go biology. And this move was really hard for a guy like me who is really digital. My culture is digital, and biology is totally different. And in our group, we had to start from scratch. We didn't know how to hold a pipette or things like this. So it was. So I don't know if that makes me the right person, but at least I'm at the right time with this bunch of new ideas, and I'm not the only one.
Fred, you say that, but I was listening to an interview. Somebody was reflecting on something that Warren Buffett said, where he said, when I'm hiring my CEOs or people in management or assessing the CEOs of the companies, I always ask, what were you doing at the age of 12? What were you doing at the age of 14? And if they were the ones who had set up a lemonade stall, if they were the ones that were trying to understand business from a young age, he thought they were the right person for the job. And if you were a person who at the age of 12 was already obsessed with technology, it sounds like you are the right person for the job, and you're the right person to do this because you were obsessed about it before you even knew what obsession was. It was just something that was interesting. That's very fascinating.
Yes, but of course, trying to mimic thinking, okay, is something that I've always been passionate about. This is a constant in my life.
So, how far along the journey are you?
Well, short answer is I don't know. So this is fundamental R&D. This is deep tech. Okay, really deep. So it may take 5 years before we get something. May take longer, or we may get, but maybe results are sooner than I expected. The big challenge is learning. Teaching the neurons to do something useful.
So, okay, so this is not a commercially ready product yet.
Absolutely not. This is an R&D effort. I'm trying to do something which has never been done before.
And how long have you been trying to do something that's never been done before?
So it's been about 5 years.
Okay, so it's been 5 years. And what were you doing before this that got you into this?
Well, before we were doing digital neurons. Okay. So we are doing about digital neurons, which are called spiking neurons. That means this is a kind of simulation of neurons, which is much more realistic than the ones which are used in the AI. Okay. And but the point is that for a few thousands of neurons, we needed kilowatts of power, of computing power, and for these kilowatts of computing power, we need twice this amount for cooling them. So we were several years in this direction until we radically switched to biology.
So, okay, this is very interesting because you said something earlier about training the neurons.
Hmm.
I think we probably take for granted how our own brain works. I mean, even if you think about something like language and the fact that we absorb that as a child as the brain is growing. But talk to me or tell me, what do you mean by training neurons? How does that actually happen? What does that do?
So training. So I'm going to use a double cap here, okay? As a computer scientist and as a, I don't know, a biocomputer scientist, okay? When you talk about training a network of neurons, whether they are artificial or biologic, it's the same. The goal is to get the correct output for a given input. Let me give you an example. You see an animal, this is the input, and you output, it's a cat or it's a dog, input, output. So this is the process of training. Now, if you do this on artificial neural networks, you have to tune all the connections between the artificial neurons. This is called the training process. Okay, and there are some algorithms which have been developed in the past 30 years to do this. In the case of biological neurons, the principle is the same. You still have to tune the connections between the neurons. So it's the same task. But the difference is that this way you don't have any direct possibility to change individually the connections between the neurons. You don't have access to this synapses. The synapses is the strength of the connection between the neurons. So you have to find another way. And the nature found a way based on reward and punishment. This is one of the mechanisms known for learning. And this is what we try to reproduce.
So is this a step into synthetic biology?
It's literally speaking, really scientific biology. Absolutely, yes. This is a correct wording to explain what we are doing. But by synthetic, we should understand that these are real, living neurons which have nothing really special compared to the neurons which are in our brain.
Now, people have been talking very much recently about the ethical implications of AI. AI is still using a computer, microchips, and, processing power. This step is a very different step. Are there sort of ethical implications in the development of technology like this?
So there are two different ethical implications here. Okay, the first one is on the biology side, because we are using human neurons. Okay, not rat neurons. Okay, so this is possible today without ethical implication because of an invention which was done about 15 years ago, which enables to convert cells of your skin into neurons. And this is what we are using. Okay, so we don't need actually to take neurons from a human being, and for fetal products, we don't need that. Okay, we can really convert these skin cells into neurons. Okay, there is some process to do this, and we do this in our lab. Now there is another ethical concern, which is the one you were referring to, I guess, which is about AI, and now what we are talking about. People say that we are doing OI, like organoid intelligence. That will be the next step after artificial intelligence. Okay, so what are the ethical implications of this? Simply speaking, it's hard to tell. At this point in time, we have about the number of neurons as a bee. Okay, so it's not much ethical implication. But if we look into the long term, I don't know. And it's always about science, is that it's pushing the lines. of what you thought was acceptable or not, and then suddenly you have something that you didn't think was possible, and then you have new questions to answer. And I'm on your side. I actually just looking for answer here.
I mean, it really sounds like the great frontier in science in many ways, especially in terms of the blending of synthetic and, well, like you're talking about actual biology being developed. So the idea of creating a brain, which is, you know, I guess like all brains, it's all about how do you train that brain? How does that brain learn? And what is that brain learn? I think the fear is that what we seem to have seen from AI when we let it run wild on the internet is that the internet is not a nice place. And the AI therefore learns some not nice behavior. And, that trains it in a particular direction instead of one of maybe kindness and humility that we probably like. So I can see where those implications come in, but I suppose we're a few years away from having that problem that we face.
Yes. I guess we have the time here to see it coming. It also brings solution. Okay. But now just to add to your thinking, there is also the question of scalability. Okay. If you think about scalability of digital processors, each time you add a new transistor, you have to manufacture it. Okay. So people talk about the Moore's law, like impressive number of transistors which are put into a processor. But in the case of bioprocessors, you use neurons, but these are living creatures. So in our lab, we multiply them. They divide automatically, I would say. They connect automatically. And the scalability is totally different. If we just wait, we create thousands, tens of thousands, or millions. It's just about waiting, and it multiplies exponentially. So we have actually always to stop the process to get it small enough so that we can work with them.
What are some of the main challenges that you've faced in the 5 years that you've been doing this?
Well, 5 years ago, when we put our first neurons on the electrodes, because we communicate with electrodes, it was living like a few hours, okay, and we didn't have any signal. And then we get the first signal, and it was like a revolution here. We were so happy. Yes, we got one spike. Okay. Nowadays, we have 16 brain organoids in real time, 24/7 on our lab, and they live for months and months, and they spike constantly, and we can stimulate them. So this is the journey that we had. And in order to accomplish this, there was so many problems to solve, so many things that didn't work. And the difference when you use living creature is that some of the mistakes, we kill them. Okay. So it's a new way to interact. I mean, with some hardware, which is called actually wetware, when your system may die actually, and you have to start from scratch again.
Sorry, you said when something goes wrong, you kill it. So tell me, What is it that goes wrong?
A bacteria, for instance. A single bacteria in our system will kill everything.
Okay. So this is more a hygiene thing rather than a wrong thought, as it were.
Yeah.
We haven't quite got to the thought point.
No, but it's about perturbation of their... This is called homeostatic system. Homeostatic system is a system which is able to regulate itself to keep in life. Okay. Our system is not homeostatic by itself. It's artificially homeostatic. So we have to keep all the conditions perfect for it to live. If you have any deviation, it dies.
Are you doing this on your own, Fred, or are you working with other people? Is this a multi-organizational effort, or is it just you with your team?
Yes, we are a team of 6 people, and that's it. However, take into consideration that the field in which we are working, which is called neuronal electrophysiology, exists since about 50 years. So we have, I mean, tens of thousands of publications that we can refer to. So there is a lot of, these people have not been working in our field of biocomputing, not at all. But many things that they have done is useful for us. And so this is for our team, but we also give free access to our neurons remotely to 9 universities, which can do some experiments, mainly to change their behavior and train them also. So they are all working on the same topic with our neurons.
And so you told us you've been doing this for 5 years. What does the future of the company look like?
So when you say the future of the company, there are two implications. There is a commercial implication and there is a scientific implication. Okay, so the future is going to stay. Well, it depends if we raise money or not. Okay, if we don't raise money, we are going, I guess, to stay like 6 or 7 people. Okay, we would not like to be much more than this, and we are going to persevere on the training side, using dopamine, using brain organoids of different types, until we get a reliable training of the neurons. If we raise money, this will be totally different. The effort will be, we will hire a lot of people to make trials in parallel with the different ideas that we have.
And how much money are you looking to raise? Because this sounds like a very ambitious project.
Yes, we're looking for $50 million.
50?
Yes.
And what kind of investor would be looking at something like this? Because this isn't the typical, hey, I've got a VC that, has a 7 to 8 year time horizon view, right? So this has got to be a different type of investor.
Yes, absolutely. So I guess this investor has to be really fascinated and want to be part of the team. And this is why actually we are not actively looking. I'm not seeking investors. I'm not, knocking doors. I'm not doing this, okay? What I'm doing is actually talking with people like you. So make the field of biocomputing and wetware computing like a known and a new field in order to inspire some people. And we already had actually some people coming to us, very rich people, saying, I've heard you, this is very exciting, I want to be part of it. So this is, I'm more into this actually.
So I see, it makes sense. You want people that have the interest, you want people that are compelled by the idea and the journey versus rather than someone sitting and saying, hey, when are you going to be able to turn a profit next?
Yes.
But this is a long endeavor, I would imagine, because you don't know whether it's going to be another 5 years, 10 years, 15 years, could be, who knows?
Yes, it's a very, if it's very risky for the VC, it's so risky for me. But the good thing is that it's not my first company. It's the second company, and the first company is still running and making a lot of profits, so I can use those profits.
I mean, it sounds like, yeah, I was about to ask you, what have you done in your past that has allowed you to have this kind of flexibility? But that's the answer right there, that you've got a revenue generating business that's generating profits, and you're taking some of that profit and you're putting it into this business.
Exactly. Yes.
Well, that's great. Fred, this has been a very interesting conversation. I thank you so much for your time and for informing us all about this new sort of wet computing.
But it was a pleasure to answer questions. I love to talk about what we are doing here. And if people want to go online, they could go to the website, FinalSpark.com, and they can see the neuronal activity in live, direct from our lab in Vevey here in Switzerland. And they will see if the neurons are healthy or not.
Amazing. I will share that link in the show notes as well so that everybody can check it out. Thank you so much, Fred.
Thanks.